Okay, hello again, everyone, and thanks for joining me for part two of this lesson on SEND-PGS, where I'll be talking about extensions of the model that I showed in the previous video. So actually, let me make room by getting rid of my video. All right. So specifically, I will be talking about how SEND-PGS models can detect and estimate different types of assortative mating, including assortment at disequilibrium and equilibrium, as well as phenotypic, social, and genetic homogamy. And I'll be going into all these terms in depth later on, so don't worry if they're unfamiliar to you right now. In addition, I'll talk about using latent genetic factors to capture full additive genetic effects, and some other model extensions that we're working on right now that will allow users to leverage different types of data and address different types of questions. So with that, I'll get started on talking about accounting for assortative mating. So assortative mating is important for a lot of reasons, not the least of which is just that it's cool and it's in and of itself. Assortment tells us about a population's culture, its priorities, its preferences. We can see how people are responding to changes in their cultural landscape. We can see evidence for that within their DNA, which is really cool. But even if that's not of interest to you, there's still plenty of reasons to care about assortment. In particular, it can really impact genetic architecture for traits. Because when two parents are assorting on a heritable trait, it means that the parents will have correlated genotypes at those trait-associated loci. And as a result, assortment can lead to increases in trait increasing alleles, or excuse me, correlations between trait increasing alleles, which are known as gametic phase disequilibrium. It will also lead to increased genetic correlations between traits if a person with trait X is preferentially choosing someone with trait Y and vice versa, and increases in homozygosity. Assortment will also result in increased genetic correlations between relatives. And because assortment entails people at the tail ends of a distribution mating with one another, it will increase the phenotypic and genotypic variances in the population. So taken individually and altogether, these factors can lead to biases and estimates from GWAS, from twin and twin family studies, and from Mendelian randomization, meaning that assortment has a number of consequences both for the genetic architecture of traits and for our ability to study the genetic architecture of traits, making it a really important construct worth studying. So to that end, here is the model that I ended with in the last video. And because assortment generally involves mates with correlated genotypes having children, I'll be focusing here specifically on the relationships between these parental genotypes. So if this is the offspring's genome, under no assortment, there will be no relationship between the paternal and the maternal haplotypes. So as shown in this variance covariance matrix, we'll have zeros on all the off diagonals, and on the diagonals, we'll just have these Ks, which again are just a constant that we're supplying. So that said, even if the individual's parents are assorting, as if there's one generation of assortment, then these parental haplotypes will start to covary with one another. So for example, the father's height increasing alleles might correlate with the mother's height increasing alleles and vice versa. And to account for that in our model, we just need to add this copath here. Copaths are a construct used in structural equation modeling, specifically for estimating assortment. And the copath in our model has a coefficient of mu, which is equal to the spousal phenotypic covariance divided by the squared spousal phenotypic variance. By including this copath here, we're allowing for all these different relationships between spousal haplotypes. And as such, these between spousal covariances will no longer be equal to 0, but instead we can make them equal to G, where G is literally just the increase in PGS covariances due to assortment. So that's how we model a single generation of assortment. And it's where some existing models of assortment end. However, if we wanted to account for multiple generations of assortment, That's also easy to do. So in addition to having these G covariances between spouses, we just need to also include G covariances within spouses as well. This is because a second generation of assortment goes back to the offspring's grandparents. So to keep using height as an example, just as one generation of assortment meant that your father's height increasing alleles were correlating with your mother's height increasing alleles, a second generation of assortment might entail your mother's height increasing alleles correlating with your mother's father's alleles. It might go back to your great-great-grandparents, even further than that. I don't know. It all depends on how long the trait has been assorted upon. But that is what we're capturing with these G terms within each haplotypic variance and within and between the NT and T PGSs within person. So this model here on the left is what we've called model 1. And again, it accounts for assortment by just allowing for all these different additional relationships within and between persons through the addition of the copath and these G covariance terms. And as you might imagine, adding in all these new relationships does come with some added complexity. So for example, in the last video, I talked about how there were 2 legitimate paths between the offspring's phenotype and the non-transmitted paternal haplotype. So there are only 2 paths which give rise to this algebraic expectation. So that's in model 0. In model 1, there are 40 paths between the offspring phenotype and the non-transmitted paternal allele. And obviously, that is a lot. And I think this is a big reason why past designs have avoided incorporating assortment altogether. But rather than having to figure out the products within each path and summing those together with all the products from all the other 39 paths, which would be really time consuming and error prone, we can implement some shortcuts. So for example, we can say that omega is equal to all of the paths connecting YP and NTP. That is, it is equal to the sum of this path plus this path plus this path. So this is a really small tweak, and it might not seem like it would do much, but shortcuts like this actually help out a ton. And it make it so that those 40 paths that I showed you on the previous slide can all be reduced down to this equation right here, which really isn't that much more complicated than the one from model 0 that we got from those 2 paths. And it's important to note, in this algebraic constraint on the right, we have these this mu and this G, which are capturing the effects of assortment. So if we use model 1, and there actually is no assortment on our trait of interest, then mu and G will both be equal to 0, and that would cause this equation on the right to be equal to the equation on the left, where we assume no assortment. All right, so that is how to estimate assortment. And now we can begin to address some other questions, like how we determine and account for assortment that is changing over time. As you can see, the previous model I showed assumes the same value for within and between spouse covariances. This means that the magnitude of assortment is unchanging, which is referred to as equilibrium assortment. Equilibrium typically implies that the trait has been assorted on for a long time, usually about 8 to 10 generations generally. However, if a trait has not been assorted on for that long and people are assorting more or less strongly on it than they used to, this is known as disequilibrium. And it will cause these pink between spouse Gs to no longer be equal to these green within spouse Gs. Fortunately, accounting for this, for having 2 different values of G is pretty straightforward. We just have to use 2 different Gs. So we have a G for between spouse covariances called G trans, and one for within spouse covariances called G cis, or GT and GC for short. So I know that this part can get a little confusing and tricky to remember. At least it is for me to remember the different Gs. So to reiterate, GT is a between spouse estimate, and it tells us about assortment in the most recent generation. So if we're speaking from the perspective of this offspring, is telling us about assortment in the parental generation. GC, meanwhile, is a within person estimate and tells us about AM in the grandparental generation and earlier. So if we want to determine if a trait is at equilibrium, we need to first test if GT and GC are equal to one another. And if they're not, we can tell if AM is decreasing, or if it's increasing based on whether GT or GC is larger. So now that we've covered GC and GT, if we want to allow for the assortment in this model to be at disequilibrium rather than equilibrium, that's easy. We just need to differentiate the variables in the parental generation from the variables in the offspring generation. So for example, we have these VEs for the parents, VE1, VE1. In the offspring, we'll use VE2. Similarly, we have VF1 for the mother and the father. In the offspring, that would be referred to as VF2. So we're just differentiating these different variables in the parental generation from what they're referred to in the offspring generation, which would allow us to account for the increase or decrease in phenotypic and genotypic variance over time caused by the disequilibrium assortment. So hopefully that makes sense. That's how we determine whether assortment is changing over time. And with that, I can move on and talk about determining what is causing the assortment. How and why are people assorting on a given trait? There are a lot of different types of assortment. There is phenotypic homogamy, which is also known as primary phenotypic assortment, in which people are mated with one another based on phenotypic similarity. So for example, tall people preferentially choosing tall people, short people preferentially choosing other short people. However, it may be that people are mating on non-heritable environmental factors rather than phenotypes. That is called social homogamy. So for example, if people were to mate based on geographic location, or maybe like birthplace location, maybe they grew up in a similar area and have a lot in common, that would be an example of social homogamy. And because these are non-heritable environmental factors, social homogamy does not impact genetic architecture, which is a really important distinction from phenotypic homogamy. It does, however, still impact phenotypic variance, so it still does need to be accounted for. And finally, there's genetic homogamy, which is when mates are preferentially choosing one another based on genotypic makeup rather than phenotypic or environmental. And I know this one is a little bit weird, given that you don't typically know someone's genetic makeup independently of their phenotypes. But evidence of genetic homogamy does actually usually point to phenotypic homogamy on a different but genetically correlated trait. So the classical example of this is genetic homogamy on educational attainment may actually just be phenotypic homogamy on IQ, if that makes sense. So understanding the type of homogamy going on is not only just like an interesting thing in and of itself, but it can tell us a lot about a trait. So for example, if we see evidence that people of high SES are really unlikely to mate with people outside their economic bracket, resulting in increased wealth disparities, it's important to understand why that is. Maybe that assortment is because people have an actual preference for others who are financially similar to themselves, which is phenotypic homogamy. Or it could just be that wealthy people are meeting one another through their jobs or through colleges, places that are generally restrictive to financially disadvantaged people. That would be social homogamy. But also it could be that they're not even assorting on SES at all, just a trait related to SES. So pinpointing the actual cause has different implications, both for potential intervention strategies in the real world, but also for the trait's genetic architecture over time. So it's really important for us to understand why people are assorting on a given trait. And that's something that we can look at using this model one that I showed earlier. So up to this point, none of the things I've shown you have required that we have observed parental phenotypes. However, if we do have observed parental phenotypes, so note these two squares, then we can compare how the observed spousal genetic covariance differs from what the expected spousal genetic covariance would be based on their phenotypic similarity. So to explain that in a little bit more depth, the observed haplotypic covariance between spouses, which as I mentioned earlier is referred to as G. This is just that. It is the covariance between these pieces of data that we have shown here in this upper right portion of the variance covariance matrix. So we're just looking at the actual observations in our data. The expected G, however, is a little bit more complicated. As mentioned, that comes from the spousal phenotypic covariances. And we obtain the expected G by path tracing. So if we trace the path between spousal haplotypes, we get omega. As I said, omega is a shortcut that accounts for all the paths between NTP and YP. So omega times mu times omega, which is equal to omega squared mu. Because mu is just a function of the spousal phenotypic covariances and variance, this version of G is also a function of those two things. So that's why this gives us the expected G based on spousal phenotypic covariance. So comparing observed and expected G can tell us the type of homogamy. If these spousal phenotypic and genotypic correlations are in line with one another, that suggests that assortment is based on phenotypic similarity. However, if the observed genotypic correlation is less than the value of omega squared mu, then it's likely people are mating on a non-heritable environmental factor, like birthplace. And finally, if the genotypic correlation is greater than omega squared mu, then they are likely mating on a different trait that is highly genetically correlated with the trait of interest. So genetic homogamy. So that is how we determine the type of assortment acting on a trait. And finally, moving along, I'll now talk about what if the PGS explains a small fraction of total trait heritability. And I'm going to go through this a little bit quickly, but I want to emphasize that just because I'm not devoting as much time to this as I did to the other things, that does not mean this is less important. This is actually one of the more important extensions of our models and is one of the biggest ways that it builds on past designs. So once again, we'll begin with model 1, which assumes that the PGSs used are accounting for the full trait heritability. There's no other genetic variable in this model other than these PGSs. However, and before I go further, of course, this assumption is untrue for all existing traits. PGSs typically explain a pretty small fraction of trait heritability, but nonetheless, this is an assumption that a lot of models make. However, we can relax this assumption by adding latent genetic effects to represent the proportion of additive genetic variance that is not being captured in these 4 PGSs. So for example, this LTM captures the genetic effects from the transmitted portion of the maternal genotype that is missing in this PGS. So like the observed PGSs, these latent variables act really similarly. The 4 latent variables also have direct genetic effects on each of the phenotypes. So each one has a path coefficient of A instead of delta. And like the observed PGSs, they also covary with the familial environment and with each other under assortment. So this is what we've called model 2 in our paper. And not to keep sounding like a broken record, but while visually model 2 is a lot to take in, clearly there's a lot going on, it's actually mathematically pretty similar to model 1. I don't have a lot of time to explain in this video why that is, but we show that in our paper in a little bit more depth if that's of interest. So one thing to note, to get estimates using model 2, observed parental phenotypes are recommended. This is because by looking at the covariance of the observed parental haplotypes with the observed offspring phenotype, we can get a sense of the full trait heritability, which in turn can be used to determine how much of the trait heritability is missing from these PGSs. With that said, even if you don't have measured parental phenotypes, you can still use Model 2. You'll just need to make an assumption about what heritability is in your population of interest, and thus what the value of A will be in your model. So that's Model 2. And finally, I'm going to go over some other extensions that we've been messing around with kind of in rapid fire succession. And I just want to preface this by saying that most of these models are versions of SEM-PGS that we've been thinking about, but have yet to formally test. So I can't speak to the validity of all of them, but I hope they still provide a showcase of the different ways that you can make changes based on the data you have and the questions you're interested in. And hopefully that'll motivate some of you to tinker with it yourselves and try to think about ways you can manipulate it to work with the data that you have. So to get started, in addition to the trio-based SEM-PGS models I've been talking about, you can also run variations for data that just have spouse or parent-offspring pairs. And if you find that you have a lot of siblings in your data set, you can also leverage those relationships to obtain some of the relevant parameters like G, because remember, G inflates relative covariance, assortment inflates relative covariances. So you can use those relative covariances to determine the value of G. So in addition to those, we've also been trying to work out a bivariate version of SEM-PGS that would allow us to look at the effect of a parental trait on a different offspring trait. So to do this, we would be replacing each of the scalar path coefficients with 2x2 matrices, which allows us to account for vertical transmission and assortment both within and between traits. And again, it's actually not that difficult to do this, even though I know it looks really crazy, because path tracing with matrices is actually really similar to path tracing with scalar values like this. There's just one additional path tracing rule that you have to follow. So in total, most of the math from our univariate models transfers over in the bivariate case. All right, and we're also looking at models that can account for differences in parent and offspring sex. So these would be able to differentiate the effects of fathers versus mothers on sons versus daughters. Lastly, we recently had a group reach out to us saying that they'd like to run these models, but that their data set has a lot of families with both parents and grandparents. So we put together a sketch of what it would look like if we wanted to run everyone together. And we also explored with them whether it would create bias to run them separately, such that the parents in one model are also offspring in another. So on that note, please reach out to us if you have any additional ideas, or like if you're curious about how SEM-PGS would work with your data or any other data types that I haven't already mentioned. We're happy to work out a solution with all of you or to give feedback on any ideas you've thought of. I've found it really cool to see the ideas that people come up with for this. So with that, I'll just say thank you all for listening. And I'm looking forward to seeing everybody in session 8 when we go through the practical. So thank you all very much.